All right, we want to use the result from the last video and take a look at the determinants of elementary matrices in this video. So first of all, let's point out that if I look at an identity matrix, it is a diagonal matrix. It's pretty easy to take the determinant of a diagonal matrix. You just multiply all the things down the diagonal. For an identity, they're all 1, and so the determinant of an identity matrix is 1. So now using that and the theorem we had from the last video, if E is an n by n elementary matrix, if E results from multiplying a row of the identity matrix by k, then the determinant of E is k, right? That's equivalent to the first row operation. Start with a determinant of 1. If you multiply any row of the identity by k, then you're going to multiply the determinant by k. So k times 1 is k. Next, if E results from swapping two rows, then the determinant of E is minus 1. Remember, swapping two rows actually made the determinant negative. Whatever it was before, now it's negative. Or the opposite of that, if it was negative, it becomes positive. But in this case, the determinant of I is 1. So when you multiply that by negative 1, you get negative 1. And the determinant of this type of elementary matrix is negative 1. And lastly, if E results from adding a multiple of one row of I to another row of I, then the determinant of E is equal to 1, right? Adding a multiple of one row to another does not change the determinant. So I had a determinant of 1, and it stays the determinant equal to 1. A couple of, here's an example of each one of those types here. I got an identity matrix where the second row here has been multiplied by k. So this is an elementary matrix. The determinant here is k. This one, the determinant is equal to minus 1. Maybe a little less obvious, but the determinant would be, let's expand across this first row here. This would be 1 times 0, 1, 1, 0, and then plus, or actually minus 0, plus 0, right? But when you do this one, this 2 by 2 determinant is 0, minus 1, and hence minus 1 for that. And lastly, this one here, in this case, it's pretty easy to see that this k doesn't do anything for you. I started with an identity matrix, I multiplied row 3 by k and added it to row 1, but this is still an upper triangular matrix, and the determinant of this upper triangular matrix is determined completely by the diagonal, not by this thing up here. And so the determinant is still 1. Okay. And lastly, for this video, just a quick theorem here. If A is a square matrix with two proportional rows or columns, then the determinant has to be equal to 0. This can be seen because if you've got two rows that are proportional to another, so say you got a row like 1, 2, 3, and somewhere else down here you've got 3, 6, 9, and then who knows what up here. A, B, C, doesn't make any difference. The thing is, this is a constant multiple of that one. So the thing is, if I say that this determinant is equal to this one, A, B, C, 1, 2, 3, and then I'm going to add a multiple of this row onto that row. So I'm going to multiply this by negative 3 and add it onto there. I get 0, 0, 0. And now I've got a determinant of a matrix that's got a row of all zeros, and that's definitely 0. So if ever you have two rows or columns where one is an exact multiple of the other, then the determinant's got to be 0. Okay, now we're going to move on in the next video to using row operations to calculate determinants of matrices.